Hi, this is David from UCR Supplemental Instruction, here to talk to you again about Physics 40B, and this time we're finally getting into some of the more interesting parts of thermodynamics with the first law of thermodynamics. So this builds upon what we've already been learning, especially last week regarding the ideal gas laws, and you're going to be using that to figure out what this all means. So first off, we'll just look at the equation that constitutes this first law, and that's that the change in thermal energy of a system is equal to Q, the energy in by heat, minus W, the energy out by work. So if we look at this PV graph, we have two states, say state 1 and state 2, then the energy difference, dE, between them is some finite value, and we can make something up for that just for this example. Let's say there's you have to have positive 4,000 joules from state 1 to get the state 2. Let's just say that's how it is. And then whatever Q and W are, they have to add together to be positive 4,000. So as you can already tell, just because we know that dE in this case, let's say, is 4,000, doesn't really tell us anything about what Q and W are. They could be anything. They could be, say, Q is 8,000 and W is negative 4,000, or Q could be negative 10,000 and W could be, well, in this case, would be a negative again, so positive or negative 14,000. It could be anything. And so what dictates what exactly those are is the path we take from one state to the other. So if we were to go in a straight line like this, that would be a one-way. Could also do whatever you want. Go maybe a path like that. You can have a path that does something sort of opposite like that. And these would all have different values of Q and W. These are kind of crazy, but it's just sort of to illustrate the point. Maybe something more realistic is there's like a sub point in here. We go up to that, and then we go across to 2. So you can also flip that over. And so anything like that, the heat and work done to go from one state to the other could be entirely different. So now we have to describe, knowing what that is, can we use PV equals nRT and some other new tools that we'll pick up to figure out exactly what Q and W are based off of some other material. So as you can probably guess, a lot of the problems around this content have to deal with you have one of these, figure out another one to solve for the third one. Maybe you don't know what the dE is, but you have Q and some hints to give you W, and you solve for W and then solve for delta E. That's going to be the general format. So now then, let's figure out how exactly we can figure out what these are. So let's start with, we'll start going from right to left. So we'll start with work. Work is interesting because there are a couple ways we can do this. If you recall, one of the major equations for this is W equals, I use some space for the integral. It's the negative integral of P pressure with respect to volume. So let's make that a little bit bigger. So this is one thing we can use. The integral of P with respect to dV, and you would have Pi and or P initial and P final. That's the general case. And in some cases, you can do this geometrically, right? If, say, this line right here, the line with arrows dE, is exactly the path taken, well, that's kind of fortunate because that adds for us, you can split this into a triangle, a right triangle here, then a rectangle beneath that, and then you can just solve for the area of a triangle, solve for the area of a rectangle, and then solve for W without doing the calculus, per se, for this integral. But that won't always be the case. So for when that's not the case, when, say, the path is something crazy like one of these, we'll need a different tool. And for that, well, we can try and work with this integral a little bit more. First off, integrating P with respect to V, if we don't know the full details of the path, kind of hard to do. So we can do a substitution using the ideal gas law to solve for pressure. So in this case, instead of P, we can have nRT divided by V, respect to V again. And still an integral. So not looking entirely simple yet, but if we take this to mean that this is an isothermal case where N, R, and T are all constants, then I'll write that as a side note. this actually does become quite a bit simpler because we can pull these out. And now from this point, we have W equals, I forgot the negative in there, negative nRT, still the integral. In this case, now we have the integral of 1 divided by V dV. And if you remember from calculus, the integral of 1 over your variable is equal to the natural log of the variable. So in this case, we can finally get a statement that is doable. W equals negative nRT times the natural log of V. And you'd still have to evaluate this. So if we have a V initial and V final, well, again, using logarithm rules, this would be VF over VI, V final over V initial. And so in this case, we have something that is, well, it's a little longer, a little less wieldy, but just as usable as, say, having like some easy geometry here, where we can use our other information to solve for the work done. And so again, if this problem was asking you how to solve for the work done, maybe it gives you Q, then you could use dE and Q to maybe solve for W. But if you need to solve for dE, well, here you go, and you already have 1/3 of this problem done. So at this point in the class, we don't have any great ways of solving for Q, but instead we can solve for dE with another simple equation. That'll get us 2/3 of the way, and eventually you'll have the case where you only have one unsolved variable, which you can solve with one equation. So it is this equation that sort of completes the circle for us. It's dE, so again, we're solving for the total change in energy between 2 points, is equal to N, that's the same N from P equals nRT, the number of moles of gas, times, and then this is a little tricky, so C here, capital C, is the molar specific heat of the gas. So you're probably already used to seeing the normal specific heat, which is in terms of mass, that being like joules per kilogram Kelvin. In this case, it would be something like joules per mole Kelvin. So instead of multiplying by a mass like we would if Q equals mc delta T, which is probably from, you probably know from like high school physics and or chemistry, this is N, so number of moles times capital C, and then dT at the end, change in temperature. So again, that coming from PV equals nRT, whatever temperature difference between these two states are, states 1 and 2. So here, actually, let me just split this up a little bit so it's a little more clear. So this is how we can solve for dE at the top. And like we said before, the total energy difference between these two states is independent of how we go from one state to the other. But what does depend on how we go from one state to the other is the heat and the work. So let's say you don't know what Q is, you have the ability to solve for dE just because you're given all these terms, and you're also given the ability to solve for W because you're given whichever terms are necessary there. In this case, W equals nRT, or probably something else, right? Because we assume that this is isothermal, and for an isothermal case here, dT would be 0, so that wouldn't work. But if you have, two of these sides of the equation, we can just rearrange for Q equals E plus W. And so again, the thing to remember here is, we're moving energy through work from one side of the equation to the other, so now it's positive. But what's important to note is whether the energy is going in or out. That's probably what's going to determine whether a value should be positive or negative for you most of the time. Relying on remembering whether an equation has a certain negative or positive part, it's really only going to get you so far, and it's easy to make mistakes. So for example, I usually find it easier to think of things in this first form, right? All we know is that the energy in and the energy out, however they come in or out, have to be equal to the total change in energy in the system. So in this case, we're just moving one of those terms over, right? So if we know that from the context clues about one of these problems, say that the heat is increasing, then, well, would it make sense if dE is, say, 0 for the work energy in through work to also be positive? So whatever gets you, dE equals 0, usually it's just easier to come back from one of these and rearrange. So that's the only tricky thing. This really just comes down to how can you solve the stop equation given these clues. And so again, this comes down to the equations, really just these two, right? So work equals negative nRT times the natural log of VF over VI, so volume initial over volume final over volume initial, excuse me, and the integral, which this even comes from, negative the integral of pressure with respect to volume, which sometimes you can just solve graphically if it's simple enough. And then this new equation, which is, as I sort of alluded to, is extremely similar to equation you probably already know. And that's that Q equals MC P, pretty common in the high school chemistry. It's essentially the same equation, except one is on molar terms and one is on mass terms. So these would be all the fundamental building blocks that you need to solve most of these problems. Things get a little more complicated, but until next video, I'd really suggest you guys become very familiar with all of these because they're going to become even more important as we build toward the end of the quarter toward cycles, thermodynamic cycles like vapor compression, Carnot cycles, all those sorts of fun things, which are just building on several of these. So you're going to be doing this problem many, many times, not just this week, next week, and definitely on your final. So that's all. Hope you learned something, and hope to see you next time.